Alright, here's the second part of the solutions for this multiple choice test. Got an object mass half a kilogram, given an initial velocity, slides across a horizontal surface. Object experiences a resistive force that is a function of velocity. So that's force is some constant times velocity, and that force is going to be in the opposite direction of the velocity. So this situation, forces that are proportional to velocity, this should make us think of air resistance and other things like that. And when you solve this differential equation, why is it a differential equation? Because, or why can it be looked at in that way? Because you turn force into mass times acceleration, divide by that, and then this is the derivative of velocity. So we want to be, the first thing you want to recognize in this problem is that it's this type of problem. And that when you solve that differential equation, you get this kind of thing, right? This exponential decay, where it decays to that, in this case, it decays to 0. And those are your constants. Okay? Which of the following is a correct expression for the net force in newtons exerted on the object as a function of time? So net force is, I would have to, this is the velocity. So force is mass times acceleration. So if I can take the derivative of this and get the acceleration, it'll give me negative alpha times beta e to the negative t, negative beta t, that is, and then multiply by the mass. So let's see what these numbers are. That's 2, and that's 3, and there's a negative sign, and the mass is a half. So I think that's going to be 3, right? So I have negative sign times 2 times 3 times a half. So that looks like, oh, and I need the negative sign is not going away, so negative 3. So it's this, B. Okay, energy dissipated due to the resistive force after a very long time is most nearly, well, it's going to slow down asymptotically to 0. So what's the velocity at time 0 when it first starts to do this? It's going to be alpha 2 e to the negative 3 times 0, so that's about 2 meters per second squared. So the kinetic energy that it has at the start is 1/2 times the mass times the velocity squared, so 1 joule. That's the energy it had at the start, and it's going to, the velocity decays to 0 after a very long time. Cart A is traveling east when it collides with cart B, which is traveling north. Cart A has a mass of 3.05. It's a strange mass to have, and this one has 2.10. Okay. 2 carts can travel together as a single object on a horizontal surface afterwards. So it is an inelastic collision, energy is going to be lost. They stick together. Okay. In one trial, the initial speed of cart A is 2.5 and 1.5 for this one. The angle relative to east that the carts travel after the collision is most nearly. Okay, so I need to figure out the momentum situation here. Total momentum before equals total momentum after. So that, and linear momentum is conserved, which means that this momentum and this momentum are conserved. So when they stick together, it has the total of this, right? So in other words, the horizontal component of the momentum after the collision is equal to this, because that's the only horizontal thing going on before the collision. So let's see what that is. 2.5 times, that's about 7.6, and then In the vertical direction, my momentum is 3.15. And it doesn't matter what the total mass is. I think we're going to need to do that maybe with this one. I just need to find the angle. Whatever the mass is, that would affect the magnitude of this, but not the direction for the total. Actually, the mass would only affect what the velocity is. The total momentum is just the vector sum of these two things. So I just need to figure out what this angle is. So I need to do tangent inverse rise over run. Make sure that I'm in degree mode. I wasn't. So tangent inverse of 3.15 over 7.6 is about 22.5 degrees. So that is choice A. In another trial, the speed of the carts immediately after the collision is 0.6, and the cards slide this far on the horizontal surface before coming to rest. The coefficient of kinetic friction between the carts. Okay, so the total mass of the carts is, after they stick together, 5.15. Is that right? No. Yes. 5.15 kilograms. And the velocity after the collision is this. So this, the force of friction is going to do work over this distance. So the kinetic energy that the carts have is got to be equal to the work that's going to be done by friction. Right? In fact, this is going to do negative work. I'm working with magnitudes here, but that should work just fine for us. Work just fine. So 1/2 mv squared is equal to, and work, this is a constant friction force, so work is equal to force times distance if it's constant force. And the force of friction is mu times the normal force, so mu times, and the normal force is just equal to the gravitational force. That's this times 9.8 times the distance. This is the force of friction. That's the distance. So those cancel out, and I just need to do 0.5 times 0.6 squared divided by 9.8 is 0.24. So 0.08 about is what I'm getting there. Alright, a block of mass m is on a rough surface attached to a spring with spring constant k. Coefficient of kinetic friction is mu. When the block's at position x equals 0, that's its equilibrium position, spring's unstretched block is pulled to that position and released from rest. The block then travels to the left and passes through x equals 0 before coming momentarily to rest at that position. So because of friction, it's not going to make it all the way to minus x sub 0 there, right? It's losing energy because of friction. Which of the following is the correct expression for the kinetic energy of the block as it first travels through the position x equals 0? Well, all of the spring energy that it has here is going to be kinetic energy here if there is no friction, right? But there is friction. So the energy equation that I would write here would be all of this energy that it has at the beginning is going to turn into kinetic energy at x equals 0, except for the fact that there's also work done by friction. So if you set it up like this and just treat this like the absolute value, right? In fact, friction is doing negative work because it's taking energy out of the system, but I'm just working with like that magnitude of it, just like in the last problem. All right, so let's see if we can make that work. This is 1/2 k x sub 0 squared is equal to, I just want an expression for the kinetic energy, so I just want to leave that as big K, and then the work done by friction is going to be the friction force, which is just, I think as they've defined things here, just mu mg, that's the normal force, times that distance. It's going to go distance x sub 0. So I think it's just this, right? That's my spring energy minus work done by friction. Yep. Which of the following is the correct expression for the coefficient of kinetic friction, mu? So when it gets to here, then we could write another equation. That was all the energy that it started with, which is 1/2 k x sub 0 squared, is equal to, when it reaches here, it momentarily comes to rest. That's its turnaround spot. So it doesn't have any kinetic energy here. It does have some spring energy, right? 1/2 k times x sub 0 over 2 squared. It's got that spring energy. And then friction did 1.5 x sub 0's worth of work here. So that's mu mg times 3/2 x sub 0. So I'm basically just using this, well, it's not the same equation, but the same energy kind of considerations here. No kinetic energy because they're there, because that's the turnaround point. So let's see what we get here. This is going to be a quarter, no, sorry, that's an eighth of a kx squared, and that's a half of 4. So this is 3/8 kx sub 0 squared is equal to mu mg. Let's write it like this. So I need to divide by this. So let's see. It looks like my coefficient is going to be 1/4, right? Because that 3 is going to end up on the bottom here. Cancel that out. 2 is going to end up on the top. So 1/4, and then I have a k x sub 0 squared. One of the x's is going to go away because of that, and then mg on the bottom. That's looking like that answer choice A right there. All right. And which of the following is a differential equation that could be used to solve for the block's position x as a function of time when it is moving to the left? Okay, and if we just take a scan, if you look at that and you read through and like, geez, what the heck is that? I don't know how to do that. Then take a quick look at the answers here. These are like mass times acceleration, right? So we just need to make a Newton's first law equation here. So when it's moving this way, what's going on with our block? Well, the spring is going to be pulling on it this way. Force of spring, and the force of friction is going to be resisting this way. So mass times acceleration would be equal to the spring force, and we're talking magnitude of spring force, right? So it would be a mistake to put the negative there. You should pause and think very deeply about that, because when we make a force diagram and we say, oh yeah, it's this minus this is the net force, we have to be very careful about whether we include negative signs. I think pretty much we never want to include negative signs when we make this little force diagram, right? These are magnitudes of things. The directions are captured by the arrows that we put in our force diagrams. So kx minus mu mg. So that looks like this. Hold on for 1 second. I'm cheating and looking at the answers, and this is the correct answer, so I need to make sure. So that has exactly the opposite signs that I have here. Why is that true? So these are positive x's. That's 0. And it's moving to the left. So the acceleration of it is this direction. Oh, that's the negative direction. Right, that's why. So right now it's accelerating in the negative direction, so that's why it's basically exactly what we have here, but it's because we did like winner minus loser, but that is the negative direction is winning. That's tricky. I would have missed that one. So there you go. That's the right answer. I'm going to fire this dart into this block, and it's going to go up that ramp, looks like. Surface of the plane, negligible friction. Projectile mass m here, big M for the block. Got that initial velocity. So we got momentum situation here, right? They move together to the right with a speed vf. Okay, which of the following is the correct expression for vf? So that's before we were worried about the ramp. So momentum initial equals momentum final. So the initial momentum is mvi. The final momentum is m plus m times vf. So that's that. These are energy things. That is not what this question is about. This is a momentum thing. So 18 is C. The block and projectile smoothly transition onto the inclined plane. Which of the following is the correct expression for the maximum height? So now it's an energy thing. So the kinetic energy that it has here will be equal to the gravitational potential energy that it has up at the top at its highest point. All right, so if we want it in terms of, just in terms of VF, I was going to substitute this expression, but that's not, they want it in terms of VF. So that's nice. They're kind of setting this up so you didn't have to get this one right to get 19, which is how it should be. And then we have M plus M, G, H. Those cancel, and I just get that H is equal to VF squared, 2 on the bottom, and a G on the bottom. Easy energy question, right? Net force F acting on an object that moves along a straight line as is given as a function of time by this. Force as a function of time. Force as a function of time. That should make you think impulse. Area of this equals change in momentum. Force is a function of time, it's impulse momentum. Oh, and there you go, there's the momentum. So that force as a function of time is here. They gave us those constants. What's the change in momentum of the object from time 0 to time 3? So the integral, or the constant's both 1, so it's just t squared plus 1. So the change in momentum is equal to this little integral right here. And that is easy calculus, folks. right, no sweat. 21, cart A, I think I'll go to maybe 22 here. That'll leave about the right amount for the last video. Cart A, mass 2m, moving with velocity, looks like it's going to crash into this, more momentum. Velocity v, when it collides, the cart initially at rest. And the collision is perfectly elastic. What does that mean? That means kinetic energy is conserved. Which of the following best describes the motion of the carts immediately after the collision? Cart A is, so I don't know how well you understand this situation, what's going to happen when they bounce off each other. But since this one, if this was exactly the same mass as this one, then this one rolls along, then this one stops and transfers the momentum 100% to this one, if it is in fact perfectly elastic. If this one is any lighter than this one, it actually bounces backward, and this one goes forward. And then if this one's heavier, then this one will continue to move forward, but slower, and this one will move also. Obviously, this one is going to be moving to the right. So let's see what all these say here. And I mean, you can do a little bit of momentum calculation stuff to figure that out if you want to, and I would encourage you to do that. But that is true that with mass m here, if this one is at rest, that's when this one stops, and that's like a boundary value for the different behaviors of the carts. So afterwards, cart A is moving to the left. No, cart A has mass greater than m, so both carts move to the right and they are stuck together. No, this isn't an elastic collision. Both carts move to the right, but they are not stuck together. That's E. All right. Ball of mass m is dropped from rest at height h and collides elastically with the floor. So again, bounce and elastically means that kinetic energy is conserved. Rebounding to its, there you go, rebounding to its original height. What is the magnitude of the net impulse on the ball during the collision with the floor? Well, if it has impulse equals change in momentum, right? So the magnitude of the impulse is going to be, it's going to get to the ground with momentum in this direction, and it's going to leave with momentum in this direction. And to change your momentum by this, you think about the signs, that you can't just do mv minus mv. Oh, it's 0. No, it's definitely not 0. You need to change it back to 0 and then this. So whatever you decide about signs, if you say, oh, well, let's say that's negative, then the change in momentum is equal to 2mv, right? And then it looks like if you see these mgh's happening, that we're just going to get what the velocity is at the floor by doing a little bit of energy. So the mgh of it is going to turn into the 1/2 mv squared of it. So v is equal to the square root of 2gh. Right. So my change in momentum is 2mv. And then you just got to figure out which one of those is equivalent to this. If you wanted to move this 2 inside the square root sign, that a 2 is the same as the square root of 4. So that's the same as m times the square root of 8 gh. Well, that's E. It's not like super common for the College Board to make finding the correct answer the matter of like doing a little bit of math simplifying like that, or unsimplifying kind of in this case. But hey, there you go. There it is.